So in today's class we are going to see some low power VLSI design techniques. In the first part we are going to concentrate on some gate level optimization techniques, and after a break of 10 minutes or so we will see some architectural level optimization techniques. Okay. We discussed in the very first class that in CMOS circuits there are 3 or 4 types of power leakages which can happen. One is known as the dynamic power consumption. Okay, that is because every gate needs to drive some load capacitance, right? And that load capacitance is because of 3 other components. The one being the drain capacitance of that particular gate itself. Okay, so from where the output is being tapped, so those transistors will have a certain amount of drain capacitance, so that is there. And then we are talking about the power which has been consumed by this particular gate. Okay, it is going to drive one or more excuse me, one or more gates. We will have an interconnect out here, right? So this is going to be a part of the syllabus. Yes. So we'll have some interconnect wires in the although on the schematic it might appear there is no capacitance, it will not contribute to any stray capacitance, but when you do the layout or in an actual VLSI chip, the interconnects do contribute towards some interconnect capacitance. Okay, and then we will have the gate capacitance of the gates being driven. So you have C inputs. So the total net capacitance are these 3 capacitance, and every time the input this voltage needs to be charged to 1. So from the power supply current will be drawn, and this node gets charged to logic 1, right? So that is again that is part of the dynamic power consumption. And whenever this node is pulled down to 0, at that time it's not taken from the power supply, but the charge available is being dissipated through the NMOS, right? So, and then we have the short circuit power consumption, where from the VDD to ground you have a direct path whenever the transistors are making a switching from 0 to 1, and then you have a leakage power, that is because some leakage through the gate, right? So from the gates and gate of the transistor, you have static power, that is even when the transistors are off, there could be some direct power supply from the VDD to ground, or in ratioed logics we have seen that there could be an NMOS here, and on top there could be an PMOS which is connected in diode configuration. In those cases there could be a static power consumption also. So we will be targeting on dynamic power consumption, okay, which happens during switching, because that is the major contributor towards power consumption. Right, if you remember, we learned, we also derived this formula where the average power is C load VDD square into F clock. Okay, so please refer to our very first class in which this derivation was done. Okay, so the average power is C load VDD square and into F clock. Okay. What we didn't discuss then was we assumed that because we were talking about in a simple case of an inverter, but in actual circuits this formula is applicable to any particular circuit, not only inverter, and also there may not be an activity in every clock, right? The output need not switch from 0 to 1. So if you see, we introduce now a new term known as an alpha, which is known as the switching activity. Okay, so this is the switching activity, means this is the probability of the circuit switching from 0 to 1. So we introduce, so this gives a more realistic power right calculation, right? So we have introduced a new term alpha t, which is nothing but it is known as the switching activity, which is the transition factor. Okay, it is known as transition factor or switching activity. Different names are there, but it essentially is like a probability of the input from switching from 0 to 1. Okay, so this is the new thing which we have modified the earlier equation which we studied. Okay, now if you see the NAND gate, which just okay, earlier we had only talked about inverter, and then we had discussed only the load capacitance out here, but there could be one load which is connected here also. So in the case of like a NAND gate, there is a capacitance out here also. So this capacitance also will get charged and it will get discharged, right? So the net power, if you see, it has to be summation of all the powers, right? So if you see here, this equation gets modified here, VDD F clock and summation of activity. So the activity out here and the activity out here will be different. So accordingly, you have to put that activity and summation of the voltage out here, and also this voltage need not go to full VDD, right? It is just a normally it might go, but from circuit to circuit it might differ. So that is why we have written CI out here and VI out here, and the corresponding activity cycle out here. Okay, so this is the more generalized form of power for any CMOS circuit. Okay, not invert. Now we are not talking only about inverters, but we are talking about any circuit. So we will have to see what are the nodes and in which there is switching, and accordingly take the power of all those nodes and do a summation of all the powers of each of these nodes. Okay. Now let's try and understand the transition activity a little more. Say for an NOR gate, if you see here, these are the inputs. Okay, 0 0, 0 1, you have a 0. So only for 0 0 you have a 1, and for all other three combinations it is 0. Now if we assume that the probability of an A being high is half, right, and B being 1 is half, that means the equal probability of an A going to 1 and B going to 1, then the static transition probabilities, that is what this alpha, we are going to come and trying to find out this alpha, right? That is when the input is going from 0 to 1. So because only when it is going from output is going from 0 to 1, the power is being consumed from the power supply. Okay, and so what is the probability of 0? We see 1 2 3 out here, so it is 3 by 4, and the probability of being 1 is 1 by 4, right? So if you multiply these two, you get 3 by 16. So this is the transition activity. Okay, so if you have the power out here, it will not be just if you for an NOR gate, it won't be CL VDD square F clock, right? It will be CL VDD square F clock into 3 by 16, right? Obviously, because if you see here, for when the inputs are changing, only once in a while it is changing from 0 to 1, right? And the probability is just 3 by 16, and hence it is not it will be more realistic to put this figure also along with the C VDD square F equation, right? So that is the reason we have calculate this. This is how we calculate the transition activity. Is this clear to all of you? Aditya, is it okay? Yeah. Okay. Now if I talk about transition activity of some other gate, and this is what 0 0, this is an exclusive OR. Okay, I have not mentioned the gate name out here, right? Okay, this is an exclusive OR, right? So 0 0 you get 0, 0 1 you get 1, 1 0 you get 1, 1 1 you get an 0. So and if you assume, see if the these probabilities of P being of A being equal to, we are taking that the probability of A being 0 or 1 is half. Okay, only in that case this equation is valid. Okay, otherwise this gets accordingly modified. Okay, so now if you see the probability of here the transition probabilities, for 0 it is 1 by 2, and for 1 it is 1 by 2. So you multiply these two, you get 1 by 4. So the transition activity for an XOR gate comes out to be 1 by 2. Okay, transition activity is 1 by 2 for an XOR gate. Okay, now if you see in general, if I say the probability of A being 1 is an PA, and the probability of B being 1 is PB, right, then 1 minus an PA is the probability for A to be 0, and 1 minus an PB is the probability for it to be an 0, right. So the equations, all these equations, and then the entire thing, probability for it to be 0, both of them being 0 will be this, and both of them being 1 will be 1 minus of this. Okay, so this is how you get the equation for NOR, and same is the case for different, right. For NAND, the probability of both being 1 will be PA into PB. Okay, initially we took both PA PB to be 0.5, but if it is not 0.5 for a circuit, it need not be 0.5, right. So it could be PA into PB is the probability that it is going to be 1, and the probability for 0 will be 1 minus PA PB. Okay, so if I take for the activities and try to find out what is the activity for a circuit like this. Here if you see here, the activity will be, right, point A, A is an the probability of 0 is 0.5, right, the probability of 1 is 0.5 again, so 0.5 into 0.5, it's become 0.25 out here, right. Now if I want to find out the activity at Z, okay, the probability out here is 0.5 for it to be 1. The probability of 1 here, if you see, there are only two right, it can be either 0 or 1, so the probability of it being 1 is 0.5, right. So both ones, okay, the probability of both ones is 0.5 into 0.5, and then the probability of 0 is 1 minus 0.5 into 0.5. So you get 3 by 16 in this particular case again, and in this particular circuit. Okay, so this is the transition activity. Okay, now our aim will be to try and minimize these transition activities. Okay, so in the overall scheme of things, if you see, if I go back to this equation, to reduce power, I can reduce alpha, I can reduce C load, I can reduce VDD, or I reduce clock. So in all the circuits which we are going to see today, one of these 4 factors we will be targeting to reduce. Okay, so that's how the low power techniques work. Okay, so let's try and first see low power gate level design. Okay, so this is nothing but, okay, the same activity cycle which we need to reduce. So this is the target thing, how to reduce this. This is what we are going to do now. Okay, and now if you see, this is a particular kind of so this is a circuit, is nothing but an ABCD, AND of ABCD. So if you implement this circuit in this manner and this manner, and try to analyze the activity cycle. Okay, now if you see here, this is 0.2 and 0.2. So what would be the activity level out here? Okay, so it is like the probability of this being 0 is 1 minus 0.2 into 0.2, right, and the probability of this being 1 will be 0.2 into 0.2. So if you multiply these two things, I'll get 0.08382. Okay, so this is the activity alpha 1 here, which is given in red. That is the activity at the gate output of A and B. Okay, so this is the activity level. Now if you try to find out, calculate the activity at this node. Okay, now at this gate, if you see, it is a 0.5, right, and what is the probability of this being 1? 0.2 into 0.2, that is 0.04. Okay, so I write 0.04. This is the probability of this node being 1. Okay, so 0.04, and the probability of this being 1 is 0.05, right. So 0.05, sorry, this should have been 0.5. Okay, my error. So it is 0.5. So 1 minus 0.04 into 0.5 into 0.04. So I get 0.0196. Okay, can you please mention again the significance of alpha activity? Can switching activity can be 0 or 1? or 1 to 0. Okay, no. See, let me go back out here. See the switching activity is always from 0 to 1. Okay, why? Because when this output node is being when the output is making a transition from 0 to 1, power is being drawn from the power supply and the capacitance is being charged. Okay, so we are drawing power. Okay, we are drawing power, okay, from VDD. So if you remember my first class, in which I told the power which is drawn from the power supply now will be C load VDD square F clock F clock, out of which, okay, this is the total power which is drawn from the power supply, out of which half CL VDD square clock, that much power will be dissipated as heat in the PMOS, and half VDD square CL F clock, that much if I remove F, half VDD square CL, that much energy will get stored in the load capacitance. Okay, and when the output is going from high to low, that stored energy is getting dissipated as heat in the NMOS. Okay, so while this capacitance is being charged to VDD, right, when this capacitance is being, when the load is being charged to high, only that time power is being drawn from the power supply. Okay, and that power supply derivation we did it in the first class, which was coming out to be C load VDD square F clock. And that is the reason we are talking about it. We are only bothered about an activity cycle alpha, which is the switching from 0 to 1. Is it okay till here? Yeah, Dilshad? Yeah, okay. Now how to compute this? How to compute alpha? Alpha is nothing but the probability of the output getting charged from 0 to 1. Now if you see a NOR gate, okay, for 3 of the input combinations the output is 0, and only for one combination the output is going 1. So the probability of the output switching from 0 to 1 here is probability of 0 into probability of 1, right? So probability of 0, okay, here is 1 by is 3 by 4, and probability of 1 is nothing but 1 minus 0, right? So 1 minus 0, so it is 1 by 4. So 3 by 4 into 1 by 4, 3 by 16, right? So this is how the activity cycle is decided, right? So we can also P0 1 minus P0 is nothing but P1, the probability of being 1, and P0 you can write it as 1 minus P1 also. You can just turn it around and write in that way also. Is it okay till here? Yeah, Anurag, is it okay? Yeah, okay, no problem. Okay, please do interrupt me, okay, in case I am going too fast. Okay, so we came here. Now if you see here, what is the activity cycle here? This is a 0.2 and this is a 0.2 out here. So the probability of this node going high will be 0.2 into 0.2, and the probability of it being 0 is 1 minus 0.2 into 0.2. So I get 0.0384. Is this now clear to all of you? Yeah, Aditya, is it okay? Yeah, okay. Similarly, at this node, what is the probability of this being high? 0.2 into 0.2, that is 1, right? And what is the probability of this being high is 0.5. So we don't take this value and compute the activity. Okay, now we have to see this is the activity cycle at this node. Okay, but what is the probability that this signal will be high? It is 0.2 into 0.2, right? So 0.4. If both are 1, only then this will be 1. So the probability that this point it is 1 will be 0.2 into 0.2, that is 0.04. Okay, and the probability of this being high is 0.05. So I multiplied 0.04 into 0.5, that is both are high out here, and what's the probability of low? It will be 1 minus 0.04 into this is 0.5. Okay, I have erroneously written as 0.05. Okay, So you get the activity cycle, and then you can compute similarly the activity cycle here. Now if I reorganize this gate out here in this manner, so you will find that okay, here this particular has gotten higher so it is 0.083 and 0.009. These activity nodes are coming to be the same, whereas for the third one this is sufficiently it is much lower than the value out here, right? So you will find as far as the low power design is concerned, this particular topology, although propagation delay wise this could result in some glitch, but if you see here this particular circuit has from power wise we have a reduced activity at this node. Okay, that you can otherwise also if you apply little bit of common knowledge, we will be able to see that. Okay, why this here if you see here this particular is C going high, probability is 0.5. Here also the D going high, the probability is 0.5, right? So you have a higher probability of this going to 1 here, right? So from 0 to 1. Whereas in this particular configuration this 0.2, so there is very less probability of this node going to 1 here, and we are taking that particular input and putting into an AND gate, right? So obviously this node will not make a very 1 transitions, although this is high, but for the output node to go 1, this also has to be 1. Okay, but that is coming from a lesser activity cycle chain. Okay, so obviously this will have lesser power. So this is what is known as when you make a circuit and we know a certain pattern of inputs are there, so then we can reorganize our gates to ensure that there is some decrease in power supply, total overall power consumption. Okay, so this is one of the techniques which is employed. Okay. So we'll take on something. Okay, now how to decide, okay, from here to here and see. So there is no straightforward technique available, but these guys, they had published paper. I went through this paper and I found that they have got they have explained one particular logic out here in gate level and how to minimize it. So this is an K map they made. Okay, now if you see here, they have grouped here all these things and they have implemented this gate. Okay, now what they found is there were two inverters which are required, right? If you see the expression for this, you have W dash and Y dash. Okay, that if you have an expression like this, you can use an NOR gate, but if you have these expressions like this, okay, that means an inverter needs to be used. And they found because of these inverters there are additional switching activities which are there. Okay, so what they did is wherever they try to avoid these kind of inverters. So if you see this expression and this expression, instead of grouping it into 4, they have split it into 2 each. Okay, they have split it into two things, they have grouped it together. Right now, obviously the number of gates have increased because of that splitting. Okay, now this so the expression has become an 3 variable instead of an 2 variable. It has become an 3 variable, and the number of groupings have increased. The number of the gates which is required has slightly increased, but the overall switching activity reduces. Okay, so that is what. So they have given a few more examples. So if somebody is interested, you can go through this particular paper. Okay, so they have just used a simple technique. First they have grouped everything, and you see it says that in case in the circuit there is no inverters, then that is the optimal solution. Okay, and in case there is an inverter, okay, then you have to try and eliminate those inverters by splitting the big 4 variable groups into 2 variable groups. Okay, that will increase the expression length. Okay, but nevertheless the total activity cycle will be reduced. So this is only for those guys who are working in the industry. In case you are encountering such issues, you can go through this paper and try to implement these kind of concepts also. Okay. Then another technique which we are going to discuss now is known as gate level design, or it is known as phase alignment. Okay. What is phase alignment or gate level design? If you see here, this is A. Okay, this is A bar and B. So this is one way of implementing it. So we are assuming a case where suppose the act B is generally high. Okay, suppose let's take one case. B is generally high. So what happens? And A is which is low activity input, and A is a high activity input. So you will find that this A nodes keep changing every now and then. And similarly, you will have an switching out here also. So and because of this switching, power will be consumed from the power supply through this inverter. Okay, charging and discharging. Okay, and if B is high, then that switching will be seen here also. Okay, continuously it will make an change out here. Now, if you try to reorganize this out here, right here. Now. If B is 0, then nothing happens here, but here there will be switching here. Now, if you try to reorganize this circuit, okay, this also again, if you see here, this is doing the same function, A bar dot B, right? It is again implementing the same function. Okay, this is NOR, it's a NOR gate now out here, right? So it is an A or B dash, the whole invert. So if you use the De Morgan's theorem, you will get this, right? So this is again this function, and this function is the same. Now suppose we are assuming B to be say B is 0 always. Okay, most of the time. So since B is 1 out here, suppose, so this output will continue to remain 0. So the transition which is being made by A doesn't get reflected in the output at all out here, right? So there is no by replacing this, in taking this particular inverter from here to here and replacing this AND by an OR gate and making this as a NOR gate, we have reduced the unnecessary switching. Okay, so this is known as phase alignment. So we'll have to see that in each circuit, if there is some lines which are making lot of transitions, so how to reduce those transitions. So these are some of the techniques which are used. Okay. Similarly, we can do this phase alignment for multiplexers also. If you see here, again A is an high activity node and there is an inverter. So every time A changes out here, there will be a change out here, right? But I may not be interested in say for a particular circuit. Most of the times I need to route a B towards the output, and B is relatively it doesn't have that much of an activity. Okay, and for a particular circuit, once in a while only I need to transmit A to the output. Okay, so these are not these are only specific to certain cases, right? So you have to analyze if such cases do exist in your circuit. So accordingly, you may want to apply these kind of techniques. So here also, if you see here, we are assuming that A out here is an high activity node, and B there is no it has got much lesser activity, and then most of the times B has to be routed to output. But having this particular configuration, although A is not being routed, because the requirement is to send A bar, we have put an inverter out here, so there will be switching. So now instead of that, we can have a multiplexer and put an inverter at the output out here, and then we are routing we have put an inverter here to invert B, right? So since most of the time now B is getting routed, but then activity of B is much lesser as compared to A, so there won't be much of power consumption out here. Then no, in that case, so we can't do much. Okay, if the activity cycle of both the A and B are high, so you might have to we just have to look for other techniques. So we are going to discuss many techniques. What actually suits that particular circuit, and depends on lot of other factors, okay, on the kind of inputs what we have and things like that, okay. Okay, and this is another thing which in you might have learnt in your VLSI class, right? In what did we learn in the VLSI class? If we want the delays, this is the pull down network of a circuit, okay. So only the NMOS is shown here. This is the output node. So these are the pull down transistors which are connected in series out here, okay. So this is like probably this will be an 3 input, okay. The extra switching of an inverter may represent inside. No, see, this is an it may not happen, right? Because if you see here, if we are not this inverter is outside the mux, okay. So this A will be passed outside through a simple, let's talk about a mux which has got a simple NMOS which is controlled by an C input. So that NMOS will be off, right? Is it okay, Dilshan? Okay, this A will be like if I have an NMOS gate here, a mux is nothing but gates, right? So if I keep that game, if most of the time if B is to be routed here, then that gate will be kept off. So now whatever A makes a transition, because you have a transmission gate, that will just block A. Okay, so that's not going to affect my inverter. Okay, okay. Okay, now I was talking about this. Okay, this is an 3 input NAND gate. Okay, so only the pull down circuit has been shown out here. Okay, you know, right, how a NAND gate looks like, and these are the 3 NMOS transistors in the pull down network. Now for delay optimization, what do we do? Suppose this makes these 2 inputs are generally 1. Okay, and this makes an transition from 0 to 1. Okay, so for delay, what we generally do is, okay, if you see this, when this is making 0 to 1, the charge which is stored here, that needs to get discharged through M3 to M2 to M1. Okay, so if you see, the RC delay will be 3R into C. Right, whereas if you reorganize these gates out here and you put it like this, and if these are generally 1, we are just talking about a specific case, if the activity cycle is less and they are generally 1 here, so it will be ground potential here. So if the moment I give a 0 here, so this will get discharged like this, right? So there will be only one RC delay. So these gates act faster, right? So for delay optimization, we keep the gate, okay, which has got greater activity as close as possible to the output. Is this statement clear to all of you? Okay, to keep the delay minimum. Okay, yeah, to keep now if you see here in this particular case, okay, this is this detailed derivations we did it in the VLSI class, but I am just telling you the concept out here, okay, without getting into the mathematics. Okay, suppose these 2 gates, okay, this is an NMOS, just the pull down network of a 3 input NAND gate, where suppose I am taking a case where these 2 inputs, okay, which is being given to M2 and M3, they are generally 1, and only this input is changing from 0 to 1. So in this case, if you see here, the output node, like when all the 3 are going 1, for a NAND gate, what happens? What is the thing which has happened to NAND gate? When all the inputs are 1, the output has to go to 0. So whenever this is going to 1, the output needs to be discharged to 0. And it will be discharged to 0 in this particular case when this this is 1, this is 1 out here, right? When it is going to 1, now this charge which is stored here, this has to come like this to get discharged. This capacitance node also has to get discharged. This capacitance also has to get discharged, because if you see when it is 0 out here, this capacitance also gets charged to VDD, this also gets charged to VDD. So if you see here, the delay will be higher, because this capacitance needs to be charged to 0 through all these 3 transistors, right? So the delay will be higher. So to optimize the delay, to reduce the delay, what I can do is I swap the inputs. Okay, so this input I have taken it to the top. Now if you see here, since these are already 1 out here, the node voltage out here will be 0 here, right? So the moment this is making a transition, this capacitor will get discharged to 0, because the ground is already available here, right? So you will find that the delay is optimized in this particular case. Is it okay? Right. So for delays, we keep this transistor which has got higher activity on the top. Okay. Now this is exactly the opposite requirement for low power. Okay. In a low power circuit, suppose this activity is low, right? Suppose let's assume these both are now here if you see, every time this makes a transition from 0 to 1, right, and 1 to 0, if you keep a transistor out here, this capacitance will get when it is switching on, this will get charged, right, and then when it is switched off, then this will be off again, this will get charge too high, right? So if you see here, it is wise to keep let me show the next slide. Okay, the one which has got more activity in the bottom for low power. Suppose this A remains off most of the time. Okay, if A remains off most of the times. Okay, so any switching which is happening at D will not take power from the VDD, right? Because after all, we want this output to be changed only when A, B, C, D, all of them are high. And for certain, and say for a particular circuit, A is going to remain off for most of the time, then I might as well keep this A in the top, right? If this is going to remain switched off most of the times, right, then this power won't be consumed at all, right? So when it is off, so it is the transistors which has got the least activity should be placed on top for a low power consumption to target reducing of power consumption. Is this okay with all of you? Why I have kept this low activity cycle here, right? Because again this is a 4 input NAND, right? So this output has to go low only when all of them are 1. And if I see, if for a particular circuit, if I find that A is going to remain it has got the least switching activity, and it is going to remain low for a long time, so I might as well put it at the top, so that this particular circuit, this NMOS circuit, is totally isolated, and we are not drawing any power from this particular node, right? So that is the reason we can do this kind of reconfiguration of the pins. Okay, this is known as pin swapping. Okay, so this is one more technique. And as a similar principle applied to the PMOS. PMOS here they are in parallel, right, in this particular circuit. Yeah, you for the PMOS circuit also we can, if I go back to my previous slide out here, if you see here, right, so if you have a this is a NOR circuit, so in this particular circuit, the one which has got the least activity cycle should be placed here, right, because this output node should be charged to 1 when both are on, right? So if particular VA signal is going to remain off for a long time, okay, I might put it here, here, right? So if suppose if A is switching high and B is switching low, what will happen is this node will unnecessarily keep getting charged high and low. We are not even interested in this particular node. So even for the PMOS circuit also, this particular concept is applicable. Okay, so there it is NAND, here it will be NOR. Okay, So we have to just see what is the one which is making most of the transitions, and then what if BC, no, you can order it accordingly. You can, whatever is the lowest switching activity, that should be placed as close as to the output. Okay. So if you have BCD, so in the previous slide 13, it's the other way. Here is it. Here we were targeting the delay. Okay, so I was telling, so there is a trade-off between delay and power, right? If you try to do the optimize the delay, then you will land up in having more power. So that is always a power delay product you have to take care. Okay, so these are just some concepts which we are discussing, which you might want to use. Okay. So here obviously we have put it here in this particular case to optimize the delay. Okay, here we are putting it the other way around. So there is a clear trade-off between power and delay. Okay. Okay, and there is something known as an glitch. Okay, now I said initially that we can reorganize the gates like this for low power, but we need to be careful about the glitch. Okay, this should not result in a glitch, and now we will see what a glitch is. Okay, now if you see here, A is going high, B is going high out here, right, and C is also going high. Now if you see here, this D, okay, after a certain propagation delay, it is going low, and E is actually high, and then it is for a small duration, it is going low and it is coming back to high, right? For 0 0 0 and for 1 1 1, for these three combinations, the output is supposed to be high only, right? But then because this gate is not placed symmetrically, okay, because of the this D signal is whereas here if you see, the C signal is going high at t is equal to 0, whereas D is going to low after a certain time gap. So in this time duration in between, right, you will find that you will find that C is 0 and D is 1, okay, in this small time duration, and that's why there is an unnecessarily transition in the output. Okay, this is known as glitch. Okay, so we need to avoid, and we have to see that. So each glitch, if you see here, the output is coming to 0 and getting again going to back, so there will be power consumed, right? Okay, so this we need to avoid. Okay, is it okay where the glitch is coming from? I have a few more slides which will elaborate that. Okay, so whenever we are making these kind of gate circuits also, glitches can be again because these glitches, okay, it is making an transition from 0 to 1 and 1 to 0, so they do contribute one proper energy. Okay, it will, this node will get this output node will get come to 0, again it will go to 1. So if you have to be very careful with glitches in the circuits. Okay, they can create other havoc also. So glitches are something which we need to take care of. So it says okay, if this structure is replaced by this structure, okay, it is going to have fewer glitches. Okay, so this is more, but you should have some technique, right? But I'll discuss that. Okay, now this is another example. I have an AB out here, right? A is permanently 1 out here, C is permanently 1 out here, and B is making a transition from 1 to 0. So B is making a transition from 1 to 0 out here. What about this AND 1? Okay, now AND 1, okay, this vertical separation, okay, this vertical separation is the transmission the propagation delay of the gates. Okay, so now if you see here, B is making a transition at this particular point, and this output, okay, is making a transition from 0 to 1 after one propagation delay. Okay, this inverter output. Okay, And what about this AND gate? This is also making a propagation delay after one gate delay here. So A is making a transition. What about this? This will actually require 2 gate delays, one from the inverter and one from the AND. Okay, so this is making a transition after 2 gate delays from here. So this is making a transition. So if I see the output, okay, again this also requires 1 gate delay, right? So you will find that in this particular space from here to here, okay, because this input is reaching after 2 gate delays, so there is an glitch which is coming out here. If you see here, this f is going to 0 and it is going to, so this is known as a glitch here, right? Now how has this glitch come? Because of this gate, see, it has to be always 1, because either there will be 1 from here or 1 from here, right? So here when 1 is going to 0, immediately after 1 gate delay it is getting reflected here, right? But now what happens here when it is going from so this goes 0, whereas this goes to 1 after one more gate delay, because there is one inverter here, right? So when this is going 0, this is supposed to go 1, but this goes 1 after one more gate delay, because there is an inverter here. So, and that is the reason in between it is going to low out here. So this is the glitch. Is this circuit understood? So what is the reason of the output and glitch out here? Okay. So if that is understood, now we have to eliminate these kind of glitches. Okay, so what do we do? So if I try to make an K map, okay, so if you see here, what is the expression out here? AB plus B dash C. So these are the ones which are corresponding to here it should be an 0. Okay, so erroneously it's written 1 here. So I make an K map, okay, the red ones, right, the 1 1 and 1 1. Okay, if I do this, this is the circuit which gets implemented. Okay, this, if I club these two and these two, okay, and these are the adjacent cells which I have left it, which I did not cater here, right? And that is the reason for the glitch. So if I make one more additional box, okay, so if there are 2 adjacent ones, okay, if I make a connection out here also, this is an additional box. Okay, so if I put this additional block, this is nothing but if you see here, this is AC. Okay, so this is an additional gate which has been introduced out here, right? So if you do this circuit gets modified like this, right? And if you see here, now when one is making a transition to 0, right? So I have A and C are permanently 1. So I have one which is coming here. So this is going 0. This will come to 1 after certain time. But I have an alternate path available for 1 out here. So there is no transition happening out here. So there is no glitch in this particular circuit. So what is the penalty? The penalty is an additional gate. Okay, and where to put the additional gate? You got to refer back to your K map, and it is not just sufficient to group all the ones, but also if there are 2 adjacent ones, okay, they need to be covered. So you can't leave like these 2 red boxes, because there are 2 ones which are close to each other, adjacent ones, okay, not the diagonal ones. If you leave the 2 adjacent ones open, covered by 2 different boxes, then there is a possibility of a glitch. So in those cases we can put an additional box out here, which results in an additional gate. Okay, but that reduces the glitch. Okay, so if you there are few more examples. Probably you can refer to my if you are somebody is interested, you can go to my digital VLSI in my web page on the digital VLSI course. Okay, there is one full lecture on glitch, okay, where I have given more examples basically on this is just for one small example. I have probably covered few more examples there, okay, and there are some tutorials also, okay, but just the basic concept is understood, I hope. Okay, is it understood by all of you? Okay, okay. Now there just I think one or two more slides, then we'll take a break. Okay. Now we can have something known as pre-computation. Okay. What a pre-computation does is, suppose there is a certain inputs which are coming here. You have a combinational logic and you have an output. Okay. But if we can look at the input combination, okay, input and a pattern, and mask some of the registers and the combinational logic. Okay, we know for these particular input combination, these registers and this part of this combination logic might be a part of many gates, right? It could be there might be several gates, and you will come to from the input combination. It is possible to just power off some of the gates. Okay. So that is the way this logic works. Okay, I'll give you an example of this so that it will become pretty clear. Suppose I have an n-bit comparator. Okay, now I have divided that n-bit comparator into 1-bit comparator and n-1 bit comparator. Okay, so this is 1-bit comparator just compares the MSB, and this n-1 comparator compares the rest of the bits. Okay, now I am giving this MSB out here, and I am putting an XOR gate. Okay, now what does that XOR gate do? If the MSB is if the MSB are not equal, right? If the MSB is not equal, can I switch off this entire block? Obviously, if MSB are not equal, then you just have to compare the MSB, right? You just have to compare the MSB. You don't have to compare the rest of the bits at all. So I can power off this entire part, right? And the output can be simply from the MSB. I can route it to the output register, right? If A is 0, obviously B is greater than 1. Only the MSB will decide, right? I can just power off the rest of the circuit out here, right? So seeing the input pattern, okay, I can decide just to power off this entire part. Okay, so this is one particular example. So this could be applicable in many other circuits also, that by looking at the input pattern, okay, you can probably suppose you have to multiply two set of data, like you have seen a Booth's algorithm, right, where we put one particular data into one register, the other bit into the now suppose a condition arises where you have to where you are doing a lot of computation, and in some particular line of the program it is coming 0 into 64, right? So will I load 0 0 and 64 and do that total cycles? No, because the input pattern says it is 0. Now I know the output will be 0, right? So I can skip that entire computation, right, depending on seeing the input pattern. So this is known as gate level pre-computation technique. Okay. So this is clock gating. Probably we discussed it earlier also. Now if you see an D latch out here, so I have an D input which is coming out here, and this is the clock. So inside the D latch, if you see here, there is I think I missed out that particular inside view of this D latch. There will be a NAND gate, and every time the clock is changing, that NAND gate gets triggered, right? So if you refer to, I think clock gating, I covered it in the very first class, or while we discussed the clock, right? So there will be some transition which is happening unnecessarily. So we can prevent this clock going into the latch by using an XOR gate. So it will just see output Q and D, and only when when D is the new input is different from the previous input, in that case this comparator is going to enable this clock to go into the D latch. So unnecessarily transitions can be avoided. Okay, this is known as gate level clock gating. Is it okay with all of you? Clock gating, yeah. I think there are another 3 slides. Okay. Okay. This is this is another clock gating thing which is shown here. If you see here, most of the asynchronous clocking. This is what asynchronous clocking, right? Asynchronous clocking means all the D flip-flops are not suppose you have implemented a counter, right, where the output of Q is given here, output is Q of given is here, output is Q is given here, right? This also becomes a counter, right? You can implement a counter here, or you can have a synchronous counter also, where clock is given to all the, but in a synchronous counter generally the power consumption is higher, okay, whereas in this but when you make an asynchronous counter, then the power is much lesser, okay. But the problem because of the asynchronous counter is, okay, you can't have designed for testing, okay. You can't see the outputs of these, right? So whereas in synchronous, if you might have learnt it in the VLSI design course about testing, right? So I'll be covering testing for VLSI in the next class. If you see here for testing, it is important that we give a synchronous clock and see when we give a test pattern and see the output from each of the flip-flop here. In this, if you give a clock like this, in that case we cannot see if one flip-flop is because the fault gets propagated, you can't really fix where the fault is, okay, in this particular circuit. So we can use an additional mux out here. So for normal routine working, okay, I give test signal is equal to 0 here. So this will Q will get connected to this like this, okay. So it will work in an asynchronous mode, which is a low power consumption mode. So whenever I want to do some testing of this circuit, then I put T is equal to high. So in that case, the clock signal will be given to each of these flip-flops directly, and then accordingly you can right, and then you can give whatever is the test pattern to the D input and then do the testing. So this is so basically two takeaways here from this slide. One is that asynchronous clocking is low power, and but however you can't have it is not suitable for DFT. Okay, DFT stands for design for testing. So in that case, we can put an additional mux here, and for normal routine working, we can have a synchronous asynchronous clocking of flip-flops, and for testing through this mux, we can remove this asynchronous clocking and put the clock to this circuits. Okay, this is the second last slide, in which if you see here, now what is happening is many circuits, if you see, when we discussed the ALU design also a few days back, you had some data which is coming here. This is doing an subtraction operation. Suppose this is doing an addition operation, and then you have a mux, okay, which will say, okay, data A plus B, this particular module will be output will be routed towards the output, and A minus B, this particular module which will be routed out here, right? So this is the general thing. But then if you see here, if you don't have a control signal out here, right, for any inputs, both the adder and the subtractor module will compute the data, okay. So and finally we are selecting one of them, okay. So rather than doing that, if you put one additional set of enabling gates out here, so if I have to do addition, then I put one set of additional gates out here also. Only then data is being fed to this out here, and this select will go high. So this select and this F2, okay, so both will activate together for an addition operation, and this will be disabled. So this additional set of hardware which we are putting in between, so that will ensure that there is no activity which is happening in the block which is not required at that particular point of time, right? So this is known as input and gating, okay. So now this is the last circuit which we are going to discuss before the break. Here we have a reduced power shift register, okay. Now if you see, you have to shift some data along the register. So I have now two set of it's an 8-bit register. I have decided now put it into 2 rows out here. Now I am giving the clock signal here to these registers, right? And I am giving a clock bar signal to these registers, and I am using half the I am reducing the clock speed to half. Okay, I am using f/2. Okay, so now if you see here, since during the positive edge of the clock, this data will be loaded out here, right? In the negative edge of the clock, okay, this next data will come here, because data is at f only, but the clock is reduced to f/2, right? But I am using the negative edge. No, because I am using the negative edge, okay, this data, the second data will be loaded out here. The third data again, and it will shift from here to here. In the next negative edge, it is going to shift from here to here. So now if you see here, this works in the positive edge, this works in the negative edge, and then you have a multiplexer. Okay, now finally the shifted data will come out here. Okay, so now what are we achieving? Obviously there is a double set of the flip-flops out here. Again 8 flip-flops okay, are used here. The advantage out here is since the clock speed has been reduced to half, okay, the power consumption in each of these blocks reduces by 50%. Okay, so you just have inserted one additional inverter and made the clock okay, anti-phase clock you have generated. So obviously this additional inverter is going to toggle every time with clock, but then these flip-flops, all these 4 flip-flops, the power consumption, otherwise if you put it in series, okay, you will have to use clock frequency f, right? So you will find here now we are using f/2 clock, so the power out here will be just 50%. Okay, so this is known as reduced power shifter register. Okay, so this is one particular way of doing. So actually this low power itself can be a full course itself, but since most of you are working in industry in VLSI domain, I thought I'll just introduce this particular class into this course, where I am just picked up many concepts from many papers and just collated it. Okay, so they may not be in a systematic manner, but at least it will give you some insight into the various low power techniques which are being used. Okay, so we'll stop here for the time being.